Okay, so I'm going to look into the processes actually, processes which control the low latitude ionosphere. We'll basically focus on the low latitude ionosphere, and then if time permits, maybe mid or high latitude ionosphere, some special cases or special phenomena which occur in those we just mentioned. But we will focus particularly what happens around our ionosphere. Our ionosphere, by our ionosphere, I mean the low latitude ionosphere. Okay, so ionosphere as such, as we have already seen, that there may be charge displacement or charge separation, and because it is a charged environment, so charge separation is possible, either due to gravity or due to some other phenomena, or means some other forces, and as a result, once the charge separation takes place, you have a current system taking place within the ionosphere. So we always have currents within the ionosphere, and those currents are determined by the ionospheric conductivities. Because for current to flow, you need a conductor. You need a conductor. If it is highly resistive, then the current will be less or current may not flow. So the ionosphere should have conductivities. And as we now know, or we shall see, that ionosphere can have or does have conductivities of its own, and as a result of which the currents flow. Okay, so let us, because why I'm looking into this currents and conductivities, because we are, or we will try to look into some phenomena which are very particular to low latitudes, like equatorial electrojet. You might have heard about that. Equatorial ionization anomaly, you might have also heard about that. So, or even ESF, equatorial, this spread F. Spread F means F region spreads, not in frequency but in height, kind of. So your phenomena, even ES is that very thin layer, but it is a very dense layer of ionization in the E region. So those are special kind of effects or phenomena which occur, and I will be trying to discuss, because our time is also limited. I will be trying to discuss that the equatorial electrojet and the equatorial ionization anomaly. These are principal effects actually. Both are present almost all the time, particularly during the day, and therefore we need to know exactly why this happens, why these phenomena take place. Okay, for that we need to know what is the field structure. We know already that there is a magnetic field. There is always a magnetic field around our globe. So, and over the equator, it is nearly parallel. And then the field lines move towards the surface of the Earth, depending on the latitude. It will be from 0 to 90 degree in deep. Okay, so this is what I have just told you, that the Earth's magnetic field being horizontal near the deep equator or above the deep equator. What I am talking about is deep equator. This is not the geographic equator. Geographic equator and the deep or geomagnetic equator. Deep means where your deep value is 0. That means your compass, the north-south, if it is free to move vertically, then it will remain horizontal. It will remain horizontal. So deep, over a deep equator, deep is 0. At 90, at the pole, it is 90 degree. So because it is horizontal, the magnetic field lines give us or give the ionosphere an unique characteristics, and it controls the dynamics of both E and F region, okay, and gives rise to interesting phenomena like at the equator and low latitude ionosphere, which I have already mentioned. Now, coming to what happens to the electrons and ions. Below 90 kilometer, you may just note down these things, small values or parameters which we will use. Below 90 kilometer, that means below the bottom of the E region. 90 kilometer is the bottom of the E region. So the collision frequencies, because we will have collision between electrons and ions. We will also have collision between electrons and neutrals, ions and neutrals. So these collision frequencies of electrons, if I write it as nu E, this is not V. This is nu E, and this is for collision frequency for ions. Because this is frequency, we are writing it as nu. So nu I. Nu E and nu I are higher than their respective gyro frequencies. All these ions and electrons will have their gyro frequencies, we know. So without going into detail of what the gyro frequency is, because all of us are aware of that, and collision frequencies also all of us are aware. So I will skip that and see that these collision frequencies are higher than their respective gyro frequencies. This will determine actually certain other things, okay? So particle motion is primarily determined by collision with neutrals. So because the collision frequency of electrons and ions are higher than their respective gyro frequencies, the motion of the particle, by particle I will mean, or we mean electrons and ions, will be determined not by their collision with other ions or ion-electron collision. It will be controlled by the ion-neutral collision or electron-neutral collision, okay? So above 130 kilometer, you look at this. This is 90 kilometer. This is above 130 kilometer. Above 130 kilometer is what? F1 region. F1 region. Here, nu E, that electron collision frequency or ion collision frequency are less than their gyro frequencies. Okay, that is fine. So the effect of collision becomes relatively insignificant, and the geomagnetic field mainly controls the particle motion. Okay? So just look at the difference between 90 kilometer and 130 kilometer. At 90 kilometer or below 90 kilometer, your particle motion, you're not yours, but the particle motion of electrons and ions are governed by their collision with neutrals. But as you go up slightly higher up to the F1 region, 40 kilometers above, you do not have these collisions controlling the particle motion. The particle motion here is controlled mainly by the geomagnetic field. Okay, so the ions and electrons are magnetized above 130 kilometer. So just 1 minute. Okay, so because it is the charged particles are now within the geomagnetic field. The geomagnetic field is also below 100 kilometer or even less than 100 kilometer. But as you can see, when you draw a magnetic field line, when you draw or magnetic field lines, as you go away from this is from the source, that means from the magnet, it is curved. So near the equator, your magnetic field lines may not be very, very effective below the E region height. Okay, that's why what we are talking about is the magnetic field lines controlling the particle motion or ion electron motion or the plasma motion above the E region height or like that. So when the magnetic field comes into play, okay? So when they are within the magnetic field or within a magnetic field, the ions and electrons will be magnetized, okay? So between 90 and 130 kilometer, what happens? Electron collision frequency is less than its gyro frequency, while your ion collision frequency is more than its gyro frequency. So between 90 and 130 kilometers, that means in the E region, something different happens. The gyro frequencies are different, or electron collision frequency, gyro frequencies should be same for electrons and ions everywhere. But what is happening is nu and nu I are different. So because nu E, that means the electron collision frequency is less compared to its gyro frequency between 90 and 130 kilometers, that is the E region, nu I, the ion collision frequency is more compared to its gyro frequency. So what happens within this region, that means the E region, 90 and 130 kilometers, this is the E region. Of course, E region does not extend to that much, 130 kilometers. It will end around 110 or 115, not more than that. But still, let us take the outer boundaries, 90 to 130 kilometers, and within that region of the ionosphere, what happens? The electrons are strongly magnetized, and ion motion is heavily influenced by collision with neutrals in this region. Okay? So what is happening? Electrons are strongly magnetized. That means the electron motion will be controlled by the field lines or the strength of the magnetic field lines or direction of the magnetic field lines, whereas your ion motion will be controlled by their collisions or collision frequency with the neutrals. So what will happen? Leading to a differential motion between ions and electrons to produce currents and electric fields in the ionosphere. This is the main part actually, or this is the main reason why you get currents or electric fields in the E region. Okay? In the F also will have currents. We'll see that later. But within 90 to 130 kilometers, that means around the E region, because the electron collision frequency is much less compared to its gyro frequency, that means it collides very less frequently, and therefore it is controlled by the magnetic field. It is magnetized. But for ions, they are much more frequently colliding with neutrals, and therefore their motion is controlled by this collision with neutrals. So as a result, one set of charged particles is controlled by what is called your magnetic field. The other set is controlled by not the magnetic field but by collisions. So as a result, there will be charge separation. Differential motion. The ions will move at a different speed. The electrons will move at a different speed. So if there is a differential motion, you always have charge separation because Say electrons are moving faster than the ions, or ions are moving faster than the electrons. So what happens? There will be charge separation, and once that charge separation takes place, what you get is an electric field will be set up between a positive charge and a negative charge. If there is charge separation, then you have an electric field set up. If they are independent and they are not close enough, then that electric field may be negligible. But if they are not separated by long distances, then an electric field will be generated, and that electric field will also produce current. So once there is an electric field, and because these ions and electrons are moving, so you have current. You have current. Okay. Now, for current, the ionosphere needs to be, for current to flow, the ionosphere needs to be conductive. Okay. So the ionospheric conductivity at above the equator at these heights or at any height will be defined by this tensor. Okay, three defined components. We have three defined components for ionospheric conductivity. Look at this. This is conductivity, ionospheric conductivity. So sigma P, sigma H, and sigma naught. Okay, sigma P, sigma naught, sigma H. Okay, what is sigma naught? Sigma naught is the parallel conductivity. Parallel means or the longitudinal conductivity parallel to the geomagnetic field. Conductivity parallel to the geomagnetic field. That means the charge separation allowing the current to flow, parallel to the geomagnetic field. That is your sigma naught. Okay. Sigma P. P is the Pedestrian conductivity. Maybe you might have heard about these terms. I don't know. Pedestrian conductivity, which is parallel to the electric field. Whatever electric field is generated, Pedestrian conductivity is parallel to the electric field. And sigma H, Hall conductivity, you might have definitely heard about this. So Hall conductivity in the direction of perpendicular to both E and H. Okay, so you have H or B, okay, magnetic field. So what is happening? You have three different types of conductivities. One, parallel to the magnetic field, that means along the magnetic meridian. The other, parallel to the electric field. We do not know exactly which direction the electric field is, so we will come to that. And Hall conductivity, both electric and magnetic fields, it will be perpendicular to the plane in which the electric and magnetic field exists. Okay. So sigma naught, and this can be calculated by using this, or these terms will have this. So N is the number of electrons, E is electronic charge. Here, E is the electronic charge. Bi and Be. Bi and Be are mobility. Mobility of ions and electrons. Okay. So this is sigma naught. Conductivity along the magnetic meridian. Sigma P, the conductivity parallel to the electric field. So Ne, this is defined by Ne. Ne is common, similar to this. So Bi by 1 plus Ki square minus Be by 1 plus Ke square. What is Ke and Ki? Ke and Ki are the ratio of the gyro frequency of ion Ki. Okay. Ratio of the gyro frequency of ion to ion neutral collision frequency, and Ke is the ratio of gyro frequency of electron to electron neutral collision frequency. This is Ki. Ki is Qi B divided by Mi nu that subscript, you may write these terms. These are also available in books. I am taking this mostly from Kelly's book. QIBMI nu I in. Nu is your collision frequency. This is IN, so ion and neutral. Here for KE, the collision frequency is between electron and neutral in the denominator. QE is the charge of the electron, B and B remaining same, ME is the mass of the electron. Here, QI is the charge of the ion, MI is the mass of the ion. So here in sigma P, that means Pedestrian conductivity, we have another term in addition to the mobilities. Mobilities, ion and electron mobilities. So this term 1 plus Ki square, 1 plus Ki square divided by this 1 plus Ke square, okay? So these terms come, these are, as we have said, ratio of the gyro frequency to the electron ion collision frequency or electron neutral collision frequency or ion neutral collision frequency. So Bi also can be written as this. Bi is equal to Qi by Mi nu I in, Be Qe by Me nu En. So here Qe by Me nu En, this is Bi, this is Be, this is Bi. So in K itself you have Bi and Be, okay? So go back to going further. This is how these collision frequencies, if you have a set of instruments which can measure your Pedestrian conductivity, which can measure your Hall conductivity, or which can measure your longitudinal conductivity or the meridional conductivity, then something like this you will get, the profile. The conductivity profiles will be like this. Look at this. I will be using this to discuss what happens at different heights, because these conductivities are not same. You can see the Hall conductivity. Of course, it is multiplied by 10 to the power 6. Hall conductivity is maximum around 120 kilometer or so, and then it reduces and goes to very little value at about 400 kilometer. But your Pedestrian conductivity, you see, we have two values for Pedestrian conductivity. One for night, the other for day. This is day, this is broken line is for night, okay? Now, when you look at the Pedestrian conductivity, you will see it is very, very strong, between 10 to the power 2 to 10 to the power 3 in the E region. In the E region, Pedestrian conductivity is very, very large, okay? So, and then it will reduce slowly around 300 kilometer or so. It becomes less by 1 order of magnitude, and then by 500, 600 kilometer, it becomes much less, 0.1 or so. So the conductivities, why I am showing this graph is, if you can just have a quick drawing, or if you want to draw, you can draw also, that this profile gives you an idea how the conductivities change with height. We have three conductivities: the Hall conductivity, the parallel conductivity or meridional conductivity, and your Pedestrian conductivity. So these three conductivities, what is happening? are not same at any altitude. At any altitude, either two of them are same, the third is not equal, or like that. So you have a distribution where both Hall and Peterson is much less is high, very high at lower heights, about 120 kilometer near in the E region. But your this meridional conductivity, that means the conductivity parallel to the magnetic field or magnetic meridian is zero or very, very small at 100 kilometer. Sigma naught is very, very small at 100 kilometer. Then it continues to increase. At 300 kilometer, it is something like 15 or so. And then no, is it 10, 11, 12 or something like that? And that it increases. The conductivity parallel to the magnetic field increases with height, whereas the conductivities parallel to the electric field and the conductivity parallel to both electric and magnetic field reduces with height. This is what the figures told you. Okay? That means in the F region, or above the F region, in the top side, only the meridional or longitudinal conductivity will matter. Sigma P will be much less, similarly this also, okay? But different scales are used for different conductivities. Values are different, but the shape is this, okay. Now what happens at higher altitudes? At higher altitudes, the electron-neutral collision becomes less abundant because neutrals are less. Because neutrals are less, so electrons will find less neutrals. Neutrals means O2 or N2 to collide, and therefore sigma naught becomes independent of density above 400 kilometer. So that is what we have seen. We have seen here, it was increasing like this. That means with density decreasing, density increasing up to 300 kilometer electron density or so, it was increasing up to say 200 kilometer or within the F1 region or below the F1 region, means F2, and then it becomes independent. This is 400 kilometer. So sigma naught becomes independent above 400 kilometer, independent of density of the ions or electrons. What happens to sigma P? Sigma P becomes maximum at altitude where the ratio of the gyro frequency of ion electron to respective collision frequency becomes 1. That means sigma P is maximum at Ki or Ke is equal to 1. Okay, and what happens? Sigma P is equal to half of Ne divided by B. Half of Ne divided by B. That is your at this point, because Ki and Ke all are equal to 1, so you can have sigma P equal to Ne by B, because both are in the denominator. If you look at the equation for sigma P, put Ki and K equal to 1, you will get Ne by B divided by 2. Ne by B divided by 2. If I go up to this equation, this one, sigma P, this becomes 1, this becomes 1, so, and this also, so Ne divided by 2, okay? Okay. In the D layer, electron contribution to the sigma P peaks and is insignificant at the mid latitudes due to very less electron density. That means at low latitudes, within the D layer, sigma P is maximum. Within the D layer, sigma P is supposed to be maximum, or electrons contribution to sigma P because this electron contribution means what? This is n, the number density. Within the d region, the negative charge is your negative charge. So the negative charge contribution to sigma p is maximum in the d region. As we have already understood that within the d region, we will have lot of negative charge. The ratio of n minus to ne sometimes becomes equal to 1 also, so large. So you have this as a maximum, becoming maximum in the d region. So what happens to Hall conductivity? It peaks in a narrow region between 90 and 100 kilometer and decreases very rapidly with height. The sigma p dominates at higher altitudes. Okay? Sigma h, you see this one. If my cursor is visible, then you can see sigma p is maximum, sigma h. Sigma h is maximum at a height around 110 kilometer or 120 kilometers, something like this. This cursor moves very fast somewhere. Okay, so this one. But after that, your sigma p takes over. After that, sigma p takes over. That means above this 120 kilometer, 130 kilometer, sigma p is more than sigma h. So Hall conductivity is maximum in the E region or just above the E region of 110 kilometer or so. Okay, 110 kilometer, middle of the E region. So in the middle of the E region, Hall conductivity is maximum. So this is how the conductivity is vary. Okay, sigma not increasing with height. That means does not depend on density above about 300 or 400 kilometer. Sigma p is dominant but decreases with density. Similarly, means decreases with decrease in density. Similarly, sigma h also decreases with increase in density. You can see here, up to about 300 kilometer or so, density will increase. Electron density, ion density will increase, but sigma h will decrease. So it peaks only somewhere here. So these are the three different types of conductivities. One, sigma naught becoming independent of density above 400 kilometer. That means in the top side, sigma p becomes maximum where your ki or k1e is equal to 1 and its value is half of ne by b. D layer sigma p peaks means electrons contribution or negative charge contribution to the sigma p is in the D layer, and Hall conductivity normally peaks around 90 to 100 kilometer and decreases very rapidly with height. Okay, so what happens? E and F region dynamos. Now I understand that all of you know what is a dynamo. So a dynamo is a device which will produce current or produce a voltage difference which will lead to current flow. So it was suggested, I have only this information I am leaving in the slides. Other references I am not giving you because it will be cumbersome also. So this was the person, Balfour Stewart, 1883. He assumed that there may be an atmospheric dynamo. Atmospheric dynamo. Why? To explain the daily variations, of the geomagnetic field. If you have a constant dynamo, if you have some constant source, then your magnetic field, the geomagnetic field on ground will also remain constant. But if it is not constant, then it will vary. Okay, so he assumed that these variations are due to a dynamo mechanism which is possible in the atmosphere. Okay, these are from your ground-based magnetometer measurements, not any ionospheric measurements. So it was just assumption that, or he proposed that within the atmosphere, he didn't say at what height or of what intensity, what direction, but he assumed that there may be something, a dynamo-like structure or an engine which is driving or influencing the current here. Because when you have a circular current, the magnetic field parallel to it within this perpendicular to it will vary. Okay, you know those things. So these geometric field variations may be ascribed to some form of a dynamo in the atmosphere. Now we know what happens, because this is 1883. Afterwards, a lot of studies have been done. So we have two dynamos, one in the E region and the other in the F region. Okay, and both are driven by winds, neutral winds. Okay, so winds drive the E region dynamo as well as the F region dynamo. Okay, keep that in mind. The dynamo is driven by your E and F region winds. The winds are not charged winds; these are neutral winds. The neutral winds, which is produced due to the temperature difference over the globe, and because of the it's called absorption of solar radiations, the temperature difference exists, or temperature difference takes place, and as a result, winds flow. Okay, as a result, winds flow from higher temperature to lower temperature, those kind of things, So both E and F region dynamos are controlled or driven by winds. Okay, but what happens? They are not similar. That's why we are talking about E and F region separately. These dynamos are not similar. Okay, they operate in separate ways due to difference of ionospheric conductivity. So this is where your influence of conductivities come, because the wind is driving the charged particle, so a dynamo is created, a current system is created. But because conductivities are different, you have different type of influence in the E and in the F region. In the E region, the same wind-driven dynamo will be flowing separately to or not similarly to what happens in the F region. Okay, so another point, the E region dynamo is primarily a daytime phenomena. Nighttime, mostly, as we know, the E region becomes very, very less. Intensity of the E region or number density of E region becomes very less at night. So sometimes it becomes so negligible that it is not detectable also with ionosons. Say in our ionoson below 5 megahertz or say 4 or 3 megahertz, it is very difficult to detect. So E region, this frequency, E region frequency or critical frequency becomes less, and which depends on the electron density. So E region electron density at night becomes very less, and as a result, it becomes a daytime phenomenon. So in the E region or within the E region, there is a dynamo which operates primarily during the daytime. If it is not some specific event, then you will have the E region current flowing only during the day. But in the F region, the dynamo can be active during the night also. Because in the F region, even at night time, your ionization never vanishes. Ionization will be still quite substantial, and as a result, what happens? You get number of ions or electrons available for conduction, and the current will also flow. So F region dynamo X both during day and night time. That means it is a 24-hour phenomena. But E region dynamo is a daytime phenomena. Okay. So what is the E region dynamo? Coming back to E region specifically, it is mainly induced by tidal oscillations of the atmosphere. Okay, many things are coming, small things, but many things. Okay, first we were looking at conductivities, now oscillations, tidal oscillations. What are tidal oscillations? Tides, you know, definitely you know tides. Tides are, okay, I will not wait for the answer because it will take some time. So, okay, let me tell you. We have tides over the ocean. Those are very common, which are visible also. You have high tide, you have low tide. Why? Because of the influence of the sun, gravitational attraction between the sun, moon, and earth. Okay? And because moon has less gravity compared to even the earth, okay, gravitational attraction, 1/6. But even then, because the moon is very closer compared to the sun, closer to the earth compared to the sun, the moon's effect on tides are, oceanic tides are very prominent. As you know, you have full moon, high tide, you have this new moon, low tide. This kind of phenomena always exist. High tide means you have the ocean water moving up, being pulled up and pushed down. So pulled up during your full moon. Full moon means what we call Purnima. Okay, during your full moon, your oceans will have high tides. The tides normal. If you are in a beach, you will see normally the winds will drive the continuous wave, which will be of say 1 meter, half a meter kind of amplitude. Normal, it will come 3 feet, 4 feet high tide. So if you are standing within the beach or near the beach, the tide, the water may come. You may be drenched till your height or maybe less like that. So that is normal. But during full moon, the tides may rise, the ocean water may rise, and it may come as high as 10 feet, 15 feet, 20 feet, sometimes it is like that. So high tide and low tide. When high tide means that ocean water will rise and come towards the beach. Similarly, during the low tide or when you have this new moon, the influence is less, minimum influence of the moon, and as a result, the tide will also be minimum, the oscillations of the minimum. So you have a tidal oscillation, 15 days time period. Okay? But we are not talking about that tide. I have written it, and these letters are also, I have increased in size. So I think all of you have seen mainly induced by tidal oscillations of the atmosphere. So where from the tidal oscillations will come in the atmosphere? Ocean, fine, we know that these tides are generated mostly due to the influence of the moon. Lunar tides, actually lunar tides, what it is called is lunar tides. But what happens in the atmosphere? Atmosphere, that means above your surface. It may be troposphere, it may be stratosphere, it may be thermosphere. What happens? Do anybody have, or all of you have some idea about atmospheric oscillations or atmospheric tides? Already basic atmosphere পঢ়োতে ক'ৰবাত পাইছিলা নেকি atmospheric tides?
ইমান ডেপথত পোৱা নাছিল।
কি কৈছা? ভালকে ক্লিয়াৰ হোৱা নাই। But what I understand is, মই যদি ঠিককে মানে শুনিছো যে
ইমান ডেপথত পোৱা নাছিল অসিলেশন।
ডেপথত আলোচনা হোৱা নাই বা পঢ়া নাই, ঠিক আছে বাৰু, আমাৰ কোৰ্চতে হয়তো তেনেকে আছে, কোৰ্চতে তেনেকে আছে চাগে। কিন্তু are you aware that tidal oscillations can be generated in the atmosphere also? Is it possible? মইতো এই লাইনটোৰ ওপৰ লাইনটো লিখিছো যে it is possible. Tidal oscillations in the atmosphere. If it is possible, how? Under the influence of what? কোৱা।
মানে শুনিছোহে, but we are not so sure of the phenomena. Means ক'বাত পঢ়োতে।
কোৱা। কোৱা।
মানে sure নহয় স্যাৰ, খালি মানে এনে শুনিছো।
Okay, let us see or let us hear what you have heard.
No.
Okay. I'll tell you. See, as I have said, over the ocean, and this water is a fluid, okay? Water is a fluid and very easy to move. Similarly, your gas, the atmospheric gas, is also a fluid. The atmospheric gas is also a fluid. So you can have waves generated within the atmosphere. We will always consider air to be a fluid, and that is true. Air is a fluid, it has viscosity, it has movement, everything. So waves can be generated within the atmosphere. Now, the basic source is your sun. So it is sun-driven. The atmospheric tidal oscillations or the atmospheric waves or tides will be sun-driven, not moon-driven. These are not lunar tides. These are solar tides, okay, solar tides. So how it happens? Because what happens when the solar radiations come down? In the thermosphere, the neutrals, O2 and N2, absorb the solar radiations. It gets heated, you know. That is the reason why it gets heated. In addition to the plasma also heats it up, but normally, even if we remove the plasma, this O2 and N2 will absorb the solar radiations and will get heated, and therefore you have a heated environment or hot environment in the thermosphere. Come down to the stratosphere. You have ozone. So that ozone layer again absorbs solar radiations and heats that region. So that's why your stratospheric height temperature is more. It goes to as high as maybe sometimes to your normal temperature over the surface of the earth, 273 degree or plus minus 273 plus minus 5 degree, around 50 kilometer height. So in the stratosphere, the heat is due to the ozone layer. And below the stratosphere, in the troposphere, water molecules. Water molecules absorb the heat maximum. Maximum absorption of solar radiations is due to the water molecules. So you have three different sources within the atmosphere. Near your surface or within the lower troposphere, you have water vapor, which absorbs the solar radiations. In the stratosphere, ozone absorbs the solar radiations. In the thermosphere, E and F region or so, O2 and N2, the neutral molecules will absorb the solar radiation. So there is a heat difference. So there is a heat difference because of which, or temperature difference, because of which oscillations or tides will be generated. So your Elysian dynamo will be driven because it is at 100 kilometers. It is not near the ocean. So lunar tidal oscillations will have no effect on your Elysian dynamo. That Elysian dynamo will be driven by your solar tidal oscillations, which is produced because of the temperature difference between your mesosphere and stratosphere, like that. So the zonal component of the electric field, next slide. Zonal component of electric field and the daytime vertical component are mainly attributed to the winds in the A region. So if you have the electric field, what we are talking about is electric field. So the electric field will be generated, and that electric field, it fills zonal component, means east-west component. East-west component, okay? Zonal is east-west, meridional is north-south. Keep that in mind. Meridional is north-south, that means along the field lines. And zonal is east-west, east-west. Either it can be towards east or it can be towards west, okay? So this zonal component of the electric, if the electric field is not exactly east-west, say at some angle to east-west or some angle to north-south, then it will have a component. And that will be, and daytime vertical component of the electric field also will be mainly controlled by the winds in the E region. As we have already said, the electrons are magnetized, but the motions of ions is controlled by neutrals in the region, in the E region. Are magnetized, the electrons are magnetized, they won't be controlled by the neutrals or collisions, but ions are controlled by collisions. So day-side ionosphere behaves like a good electrical conductor where currents are due to lower thermospheric tides, which are mostly diurnal and semi-diurnal tides. Depending on latitudes, depending on the position on Earth, you can have diurnal as well as semi-diurnal tides. Okay. Now, what is diurnal? Diurnal is once in a day. Once in a day means within 24 hours. If it is a wave, then that will have a peak, one peak within 24 hours. Semi-diurnal means within 24 hours, it will have two peaks. It will have two peaks. That means 12 hourly, and the other is 24 hourly. Okay? So what happens? You may have also other tides, say diurnal, semi-diurnal, then tridiurnal kind of thing. Other components may also be possible. Why? Because if you look at the thermospheric tides, how it behaves or how it oscillates, it will be similar to a square wave. Not exactly similar, but it will be similar to a square wave. So you can break it up two components. You can do a Fourier analysis of the tides or the amplitude of the tides, and you will get the 24-hour component, 12-hour component, and like this. And these components, amplitude will vary with latitude. Near the equator or over the equator, it is mostly diurnal. Semi-diurnal will be meaningful or kind of dominant when you go towards higher latitudes. Okay. So therefore, the tidal E region wind will be given by this U. We'll normally write U, that capital U for wind. It is a function of both R and T. R is the distance from the center of the earth. Distance from the center of the earth. R is distance. T is time. So across Earth's magnetic field causes a dynamo action that drives a global current system expressed as this J sigma RT and this. This is the current. This is the current, which is your conductivity. This conductivity contains all the conductivities URT cross B. URT, that means this is the E region wind into B or cross B. Okay, so this is the current. This current is generated. This current is generated because you have conductivities, which is a variable with respect to both R and time. Similarly, wind is also variable with respect to both R and T, and B is constant. So you have this J. Since sigma RT and URT are functions of R, so the current J may not be divergence free. May not be divergence free means it will diverge. It will change with time, or it may change with distance. Diverse. Okay. So to make it divergence free, you have the total current should be equal to 0. So we can write it like this. We can write it like this. Del dot, the same equation, sigma ART plus URTB, but we will make it equal to 0. The divergence will make the divergence equal to 0. And if we make the divergence equal to 0, then this ERT, this E, electric field, with respect to distance and time, will be a very complex quantity. Very complex quantity because it depends on the tidal winds, and also it will depend on the conductivity. Because you take this, if this sigma ERT becomes equal to minus of this sigma URT cross B, okay? So all this will be there, sigma will be there for E. So ERT becomes equal to minus URT cross B, okay? So URT, it is the wind component, and you have the tidal wind component because conductivity is varying with height or yes, with height only. Your equation becomes very complex. Okay, divergence, if we need to make the divergence equal to 0. Okay, so these are the conclusions for that. So I think we can start already. We are 5 minutes past your scheduled time. So okay. So what is happening is, what we have discussed so far is, because of the difference in conductivities and because of the tidal oscillations, we can have, or there is a current in the E region, which is basically diverse, or you can say it is not divergence free. But if we consider it to be divergence free, even then that electric field is, the equation for the electric field or the electric field itself becomes very complex because the conductivities vary as well as your wind varies. Okay. So this much for today.
Yes, sir.
Okay.
Sir.
Yes.
Sir.
Sir?
What?
Sir, Hargreaves' bookত মানে class the assumptions of Chapman theory that eta bostu mention ase the atmosphere is considered to be having constant scale height. So constant scale height hetu mane physically meaning to ki hobo was he trying to formulate the theory of a region which is isothermal because scale height is
Isothermal
mg by
as well as one space, as well as one species. So
isothermal.
kT by mg. So if you have isothermal plus more or less one species. Not more or less. He considered only one species. So one species means your m is fixed. If it is isothermal, then T is also fixed. So kT by mg remains same, except for the very small variation in G.
Yes, that G is also means we are taking more
or less, yeah, above the surface of the Earth from 200 kilometer to 300 kilometer, how much it will vary? Very, very insignificant.
Okay, sir. Thank you, sir.
Okay.
Thank you,
Yeah.
sir.
Yeah.
Very এওঁলোকৰ বেলেগ ক্লাছ আছে মই ক্লাছৰুমত মেটেৰিয়েল দিছোঁ হা বেলেগৰ লগত শ্বেয়াৰ নকৰিব